So we have our Lagrangian, so we can move on to the next stage of the question, and that was to derive the equations of motion. So we will consider first theta 1, and we then need to take our partial derivative with respect to theta 1 dot. So I have my Lagrangian, so m1 L1 theta 1 dot, and then there's a term m2 L2, no, m2 L1. So easy to get these mixed up. Theta 1 dot, and we also have an m2 L1 L2 theta 2 dot. So this comes from the term that involves both theta 1 dot and theta 2 dot. So the theta 2 dot remains. And then there's a cosine theta 1 minus theta 2. And I'll just make sure I have my factors correct. That's m2, yes. And that is it.
Shouldn't it be L1 squared?
L1, oh yes, thank you, L1 squared. Yeah, I was so worried about the subscripts that I dropped the exponents. Yes. So then we need the time derivative of this, d by dt, of di L by di theta 1 dot. And now we can see there's going to be quite a few terms. So m1 L1 squared, theta 1 double dot, plus m2 L1 squared, theta 2 double dot, plus m2 L1 L2, theta 2 double dot, cosine theta 1 minus theta 2. But because this is a total time derivative, we then need to take the time derivative of that term. So we're going to end up with a plus m2 L1 L2 theta 2 dot. And then we get a minus sine theta 1 minus theta 2. And there'll be a theta 1 dot. And then we also have a term that's minus sine theta 1 minus theta 2 minus theta 2 dot. I'm just going to double check that I've done all these steps correctly, because if I haven't, things will get absolutely horrible later on. Minus m2 L1 m2 theta 1 dot minus theta 2 dot sine theta 1 minus theta 2. Yes, okay, that's correct. Horrible looking expressions, but rather straightforward to work out, just long and complicated. So the other term that we need is this partial with respect to theta 1. So I return back to my original Lagrangian, and so I have a term that will arise from the kinetic energy part. So there will be an m2 L1 L2 theta 1 dot theta 2 dot. And then this is a partial with respect to theta 1. So there's a minus sine theta 1 minus theta 2. And then I have now contributions that come from the potential energy term. And here I'm just going to cheat and refer back to my notes. So there'll be a minus m1g L1 sine theta 1 minus an m2g L1 sine theta 1. Okay. So now that we have all those terms, we can put together our equation of motion. I could write this whole thing out on the board. I don't think I'm going to do that because it's not overly illuminating, and everything that we need is right here in front of us. So it's these terms minus these terms, and we set all that equal to 0. So the first thing that we'll notice is we have coupled nonlinear equations. So already for the first mass, it is a horribly complicated differential equation to try to solve. If we look at the expressions for theta 2, we go through exactly the same steps, take our partials with respect to theta 2 dot, take our partial with respect to theta 2, and combine everything together. And so here I will just, again, write down what the final expression would be. So we have an m2 L2 theta 2 double dot plus an m2 L1 L2 theta 1 double dot. Then there would be a cosine theta 1 minus theta 2 minus an m2 L1 L2 theta 1 dot squared sine theta 1 minus theta 2, and that would have to equal m2g L2 sine theta 2. So it turns out to be a little bit simpler, although it's still a coupled nonlinear equation, but it's a little bit simpler than the equation that would be in place for theta 1. But still, at this point, these would be very difficult equations to solve unless we make further simplifications. But those are the equations of motion.